get started. Okay, so it's a pleasure to welcome Christian Voigt from University of Glasgow, who will speak about quantum Cuntz-Krieger algebras. Please go ahead.
Thanks very much, and thanks very much for the invitation. It's very nice to come to Argentina. Well, it's only virtually, unfortunately, but still, well. So yeah, I'm going to speak about a joint project with Mike Brennan, Kari Eifler, and Moritz Weber, which is about a generalization of Cuntz-Krieger algebras. And yeah, so this is all happening in the framework of C-star algebras, but some of these constructions would make sense at an algebraic level as well, and would also lead to some families of algebras there. So yeah, anyway, so what I plan to do is I will probably spend some time to tell you about the key ingredient in this whole construction, which are quantum graphs. And yeah, they are a generalization of finite graphs and have appeared recently in a number of contexts, and I think provide a very interesting playground to try things. So it's kind of involving both ideas from combinatorics and also ideas from operator algebras. So that's what makes this interesting. And then I will tell you about how to associate to such quantum graphs certain C-star algebras, and the model case, in a sense, is how you go about constructing Cuntz-Krieger algebras associated from an integer 0-1 matrix. And then I'll tell you some examples and some things that we can say about these algebras, and perhaps also indicate some questions and open problems. Okay, so let's perhaps first start with a little bit of graph theory, just to set my notation and remind you of some terminology. So I'll be interested in graphs, by which I mean finite directed graphs. So we'll have finite sets of vertices and edges, and the edges are directed, so they go from the source to the range. And that's encoded yeah, by these maps as I've written down here. So the typical way to visualize this is by drawing pictures as on this slide. And one thing I should mention is that I'm using a slightly non-standard convention in that I will allow graphs to have self-loops. So yeah, that's usually excluded when one speaks about simple graphs, but for me, yeah, that will not be the case. Okay, right, so that's a rich combinatorial structure, and you can ask tons of questions about graphs and phrase things, problems in terms of graphs. An equivalent way to encode the structure of a finite graph is to write down its adjacency matrix. So that's just a matrix indexed by the vertices of your graph and has entries in 0, 1. And yeah, you put an entry 1 exactly if there is an edge connecting the two vertices. And I guess one has to agree, yeah, the convention regarding source and range. Yeah, so it doesn't matter too much. Whatever your convention you choose will work. Okay, and okay, just again, this example from the previous slide. And I guess if you look at this matrix, you can recover which convention I'm using regarding source and range. Anyway, so that's the structure that one is studying in finite graph theory, or one of the structures. And quantum graphs are a non-commutative generalization of this. And as often in non-commutative geometry, to arrive at a non-commutative concept, you first have to rephrase your classical commutative concept in such a way that it no longer involves any commutativity. And once you have that, you can then make things non-commutative. So that's the same strategy here. And so we will first rephrase graphs in a slightly more complicated way. And this goes as follows. So the set of vertices is going to be replaced by the algebra of functions on that set. So we're only looking at finite things here. So this algebra will just be a finite dimensional commutative C-star algebra and spanned by a family of projections, which I will denote by P sub V. Then, okay, in a sense, what comes automatically or canonically with that is the uniform measure on this finite set. So at this point, it may not be clear why we want to consider this as part of the structure, but I'll perhaps say a bit more about this later on. So in any case, we have a natural state here. And again, the way I've written this is probably more complicated than necessary. It's just the trace corresponding to the uniform measure on our set of vertices. And once we have that, we can form the Genome space. Again,
sorry.
Yeah.
If I think of B as a sum of copies of C as many as there are vertices, right? So I take an element lambda sub B and apple of that. Then the trace is the sum of the lambdas, or what is?
Yeah.
Okay.
Normalized. So I want it to be normalized. So
divided by the number of vertices.
Yeah.
Okay.
Exactly. So exactly, that's what it is. Okay, once we have that, we can form the Genome space. Again, things are finite dimensional, so nothing much is really happening here. It's just viewing this finite dimensional algebra as a Hilbert space at the same time. And the key point is that we want to view the adjacency matrix. Well, this is a matrix indexed by the vertices, but we want to view it as an operator on this L2 space. So that's why we want to include this Hilbert space structure. Okay, so that's in a sense all the data that we have got. And as I said, I mean, the matrix already captures all the information, so we haven't lost anything clearly. But how can we phrase the property that A is really an adjacency matrix in terms of the data we've got? So this is what there's probably several ways in which you could do this, but the way we are going to do this is as follows. Notice that a matrix A is the adjacency matrix of a graph in the sense that I explained if and only if it has entries in 0, 1, right? That's basically clear from the setup. And having entries in 0, 1 is the same thing as being an idempotent with respect to the Schur product. So the matrix A being idempotent with respect to Schur product being the naive matrix product where you just multiply entry-wise. not matrix multiplication, but entry-wise multiplication. Okay. And I claim that the sure product can be expressed purely algebraically in terms of the data that I have assembled. So let me show you how this works. Well, what is the data we've got? We have an algebra, which comes with a multiplication map, but the algebra is the same thing as the Hilbert space. So I'm abusing notation here, and I'll write the multiplication map as map on the Hilbert space level, which I can do. And once I do that, I can look at its adjoint. Okay, and I've written down the formula here. So multiplication, that's how you multiply these orthogonal projections. And the adjoint of that with respect to the Hilbert space structure coming from the canonical trace is just given by this formula. Easy to check. So that's what you get. And then I claim that the sure product of two matrices, if you view them as operators on L2 of B, is given by this formula. So, and on the right-hand side, only the algebraic structure appears. So let's have a quick look why this is. So how can we check that the two sides are the same thing? Well, we have to check that they act in the same way on our Hilbert space. So it's enough to check that on the basis formed by these projection PW. And then, okay, here in this first equality, I'm just plugging in the formula for n star. So that cancels out the dimension and leaves us with this expression here. Well, applying x and y, the matrices x and y. And then I need to multiply. And well, PU times PV is 0 unless U equals V. So this sum here reduces to this expression. And that's really the same thing as applying the sure product of x and y to PW. So that's how this works. So sorry for, I mean, maybe I'm going too slowly, but it's at least, it can be confusing to have, I mean, this Hilbert space structure and the algebra structure, and in a sense, one has to be a bit careful to.
Sorry, as a slow student of your class, why do the p's come on the left of the x and the y and not on the right?
Yeah, well, either way, I mean, the x, uv, uw.
Because you write the matrix backwards. When you wrote the operator, you used the, well, you set up your, I was happy that you set up the end and the source and target of the arrows right, but then you transpose the matrix on me.
I think, to be honest, I think I might have even changed conventions here. I'm not entirely sure. Yeah, it could be that I should have done it the other way around. In any case, the entries of the matrices are scalar, so I can write it, well, modulo correct choice of conventions. It doesn't matter whether I put the P to the left or right. Yeah, sorry about that. Yeah, so you said the right convention. That's, yeah, I'm not sure. I don't know what the right convention is.
Well, you know, I have
your convention.
Yeah. Well, you know this statement. There are two ways to do things: the right way and my way, and they're both the same.
Yeah, I like that. Okay, so well, now with that in place, I can tell you what a quantum graph is. And this goes back, so the definition I've written down here goes back to work of Musto, Reuter, and Verdon, and all the 7 authors listed next, which I'll not read out. It's not exactly what's in these papers because there are various small things you can change in your graphs. You can look at undirected graphs. So that's what these papers are doing. They're not looking at directed things and some other small changes. But in spirit, this is really going back to these papers. So what is the definition? We basically allow our vertex set to be a finite dimensional, possibly non-commutative C-star algebra instead of a bunch of points. So we start with a finite dimensional C-star algebra B, which we should think of as, well, functions on a bunch of quantum vertices, whatever you want. Then we also keep track of a state on that algebra, and there's, of course, there is a lot of choice. You could look at a number of states, and for the time being, I want to fix the canonical tracial state, which comes from, well, embedding B into endomorphisms and then taking the matrix trace there. So again, I'll probably come back to that a little later. So the key ingredient is this quantum adjacency matrix A, which is an operator from the L2 space to itself, and which satisfies this condition here, which is basically just saying that it's a sure idempotent. Of course, now sure product is something more complicated since our B is no longer commutative, but that's at least how to think about this condition.
Sorry, the psi appears in the definition of the inner product that you put on B, right? Yes,
exactly. So that I should have made that clear. In a sense, that's how this enters into the third condition, because we form L2 of B with respect to psi, and that affects the map M star, right? So M will always look the same, but M star depends on which state psi I choose. And you're exactly right. This is how this state enters the definition. Any other questions at this point?
But sorry, if you write B as a finite sum of matricial algebras, then isn't there a unique psi determined by what? I mean, by the condition that you put, or not?
Yeah. So I've picked one state. This what I call the canonical tracial state. So that is uniquely determined by B. So in a sense, there is no choice here. So yeah, later on we will allow this state to vary. We'll allow other states as well. But for the time being, in a sense, there is no extra data here, just the algebra and this operator. So maybe this is confusing here. Yeah, but in principle, one could take any faithful state, and one could come up with, well, one could call this a quantum graph. Any other questions? Well, if not, let's first observe that with this in place, what I showed you on the previous slides is basically saying that a quantum graph whose underlying C-star algebra is commutative is the same thing as a graph. So just translating back and forth. So that's really, there's nothing new there. So things become interesting if you allow B to be non-commutative. And I'll show you, well, some examples. So actually, even in arbitrary finite dimensional C-star algebra, there's two things you can always do. One is form an analog of the complete graph. So that would be the graph where all vertices are connected in the classical case. And the analog of that would be to form a very specific quantum adjacency matrix, which is given by this formula. So if B is commutative, that will be the all one matrix, but in the non-commutative setting, this looks a bit different. The second example is perhaps even simpler. That would be the trivial graph, and that would correspond to the identity matrix. And now this may, again, I have to stress that I allow self loops in my graph. So classically, the trivial graph would be the one where you only have the self loops and you have all of them. So yeah, in a sense, you can always pass. I mean, these self loops are a bit of a pain in the neck, but my convention is in a sense that you always include the self loops here. So anyway, and then there is other things you can do. So look at diagonal matrices, and yeah, you can check that there is a certain condition on the trace then for these coefficients. However, what's probably not so clear at this point is what else, or in general, how to think about these quantum adjacency matrices, how to come up with examples, because this sure idempotent condition is a bit hard to decipher. So, and in a sense, the nice thing is that there is an alternative picture of how to study quantum graphs, where you can see the structure, well, I'm tempted to say more easily. It depends on exactly what questions you're looking at, but a useful alternative picture, which at least allows you to see that there is a lot of possibilities for constructing quantum graphs. And that's what I want to discuss next. In a sense, that is the original definition of quantum graphs, which goes back to work of Weaver. And it starts from the observation that the graph is also determined uniquely by the edge relation. So you look at the relation on the vertices, which just contains the edges, right? So that gives you a relation. And then you can look at a subspace in the operators on the L2 space of the vertices spent by the corresponding rank 1 matrices operators. And if you do that, then what you will find is that the corresponding subspace in matrices on L2 of E0 is a bimodule over functions on E0, which is the same thing as its commutant. And that, in a sense, motivates Weaver's definition. So you start.
But the S sub G does not appear in the definition.
No. That's true. So these are independent things. In a sense, the first half of this slide is just background motivation, and the definition is just independent of that. But the way to think about it is this set S in the definition. A prototypical example would be S sub G, where G is a graph. And B would be functions on the vertex set as we had before, represented by multiplication operators on L2 of E0. So that would be an example of quantum graph in Weaver's sense.
So how do you visualize B prime, B prime?
So B prime is just B in this case. The commutant of the multiplication operators are again multiplication operators, diagonal operators, if you like. And the space of all these edge operators is closed under multiplication by such operators. So therefore it forms a bimodule. So you can multiply things and you stay inside this subspace. Does that make sense?
But if V prime is V, I understand what it means. Yeah.
Okay. So, I mean, B primed is the commutant. So that's another algebra, and you can still ask for things to be bimodular over that. So, yeah, with respect to the natural multiplication action so natural multiplication in B of H. Yeah. Anyway, I don't want to dwell too long on this, just to say that there is a comparison between these two approaches, and they are basically equivalent. And this slide very quickly tells you how you pass from one picture to the other. And okay, again, in a sense, one has to be a bit careful with the precise setup of what kind of graphs or quantum graphs one wants to consider. Okay, maybe I shouldn't even get into the details of this slide. The point is, what this shows is that there is a large supply of quantum graphs. So even if you take B to be, say, n by n matrices, in this case, and you say, let's say we take the Hilbert space to be just row vectors, then the commutant would be the complex numbers. So bimodules is the same thing as having vector space decompositions of your matrix algebra. And there's certainly a lot. So there's a lot of things you can do. And if you look a bit more carefully, then you see that even if you take B to be 2 by 2 matrices, you find already uncountably many non-isomorphic quantum graphs, and there is even, so there's also uncountably many possible spectra, and yeah, one can say in more detail what kind of things are possible. Even in this very small case of 2 by 2 matrices, things already get quite interesting. Anyway, you may wonder why on earth would people study such quantum graphs? So they have appeared in different contexts, as I already said. One being connected to the so-called graph isomorphism game. That's well, maybe I won't get into the details there, but this is primarily about graphs. But if you want to understand the quantum symmetry of such graphs, then it's actually natural to also allow quantum graphs in the sense that I've described. And then there's ideas from quantum information theory where these quantum graphs appear. I won't get into the details there, but just to say that yeah, so there is independent interest in studying these beasts. Okay, and at the same time, plenty of interesting questions you can ask. So basically, any combinatorial result for graphs which can be phrased in a way which generalizes, you can ask for quantum graphs, and typically the answer is not obvious, and you have plenty of things to understand there. Okay, but let me now move on and tell you about our project. But okay, before doing that, let me quickly mention one generalization. I already hinted at that in the definition, instead of looking at this canonical tracial state, which comes automatically with our algebra B, one can look at other states, and that can be interesting. So if one thinks in terms of quantum groups, that's actually very interesting. But just to say that there is a modification, a more general way of phrasing, or this extra flexibility of varying the state, and that gives you even more examples, if you like. So even more things to play with. But I think for the rest of the talk, we won't need any of that. So yeah, and I think we will mainly be looking at B being a full matrix algebra and psi being the canonical trace on that algebra, and that already turns out to be quite interesting. Okay, so as I said, we want to cook up an analog of Cuntz-Krieger algebras in this setting. So let me briefly remind you what Cuntz-Krieger algebras are. So we start with a matrix with entries in 0, 1. And then the Cuntz-Krieger algebra associated to this matrix is the universal C-star algebra generated by partial isometries S1 up to Sn with mutually orthogonal ranges satisfying the so-called Cuntz-Krieger relation, which I've written here in this formula. So partial isometry, just to be clear, partial isometry in a C-star algebra is an element S, such that S star S is equal to S. And yeah, the range projections are S star, and yeah, orthogonal ranges means that these projections are multiplied to 0 if you take two of these guys. So, well, just two examples here. If you take A to be the identity matrix, then the algebra you get will be a direct sum of copies of functions on S1. That's basically because your isometry will be a unitary, or almost a unitary in this case. The other extreme, if you take A to be the all one matrix, then the algebra you get is the famous Kuntz algebra. So yeah, which you probably have seen before. Okay, now we want to generalize this, and as you can imagine, the basic ingredient here is a matrix with entries in 0, 1, and that's exactly the data which encodes a directed graph. So in a sense, what we are going to do is we will replace our matrix here with the adjacency matrix of a quantum graph. So that's the plan, but before getting there, there is a small issue. If one wants to do that, remember, in a quantum graph, in a sense, the vertices are replaced by matrix algebras, and that means that instead of looking at partial isometries, we want to look at what I call matrix partial isometries, generating our algebra. And what I mean by matrix partial isometry, take a C-star algebra D and take a matrix with entries in D, and then a matrix partial isometry is just such a matrix which is a partial isometry in the matrices over D. So I've written out this condition here. Yeah, does that make sense? Okay, now that is in a sense how we make things non-commutative, or how this non-commutative aspect of quantum graphs will enter. But there is an obvious problem if you do that, and if you compare with the definition of the Cuntz-Krieger algebras, mutually orthogonal ranges, if you have a bunch of such matrix partial isometries, and if they have different sizes, if the matrix size varies, and we certainly want to allow that, then it doesn't quite make sense to speak about having mutual orthogonal ranges, because projections live in different algebras. So it's not clear how you would even compare. So the way out here is to forget about mutual orthogonal range projections. And that's what I mean by liberating Cuntz-Krieger algebra. So I'll tell you about this in a second. The terminology here is motivated again from quantum groups, where, I don't know if you have come across this before. So there is a whole machinery which allows you to liberate matrix groups. So the most famous one probably being the symmetric group. There is the so-called quantum permutation group. And that is obtained by, in a sense, dropping relations, any unnecessary relations. And here, in a sense, we are also dropping some relations which we don't want. So that's where this terminology comes from. Anyway, so liberated or free Cuntz-Krieger algebras, that's the following thing. We take the same input, an integer matrix with entries in 0, 1. And the definition reads almost the same as the Cuntz-Krieger one. The only difference is that we do not require mutual orthogonal ranges for these partial isometries. And that changes things in general. So in the two examples that I've listed, instead of having a direct sum, in this first example, you now get a free product of the corresponding algebras. In the other example, nothing changes. So yeah, in a sense, because there is only one vertex, so there is no condition to be taken care of. But you may wonder, okay, so of course one can make this definition, but how is it related? How does it change the story? And so more precisely, what is the relation between these free Cuntz-Krieger algebras that I've just introduced and Cuntz-Krieger algebras, the real Cuntz-Krieger algebras in general? That's not so clear. I don't have a full answer to that. So sometimes these algebras are just the same. Sometimes there is a kind of free product versus direct sum relationship. What we can say is that, well, there is always a quotient map. So in the Cuntz-Krieger algebra, you just add more relations. So there is an obvious quotient map, and at least at the level of K-theory, that doesn't change things. So more precisely, this map is a KK equivalence, if you're familiar with KK. Okay, now let's get to quantum Cuntz-Krieger algebras. And on this slide, I will just throw the definition out, and this will probably look hard to decipher. We take as our input, we take a quantum graph, and we want to associate a C-star algebra to it. And I will probably not dwell too much on trying to explain the precise meaning or how to read these formulas. There are two conditions, in a sense, on what I call a quantum Cuntz-Krieger family. And the first condition, condition A, that is kind of encoding that the algebra is generated by matrix partial isometries. So this condition A is kind of a partial isometry condition. And condition B is the analog of the Cuntz-Krieger relation. So that's how to think about this. And then, yeah.
Yeah. Why do you need any sister algebra D? I mean, wouldn't it suffice to take just the full operators in Hilbert space? Because any D is inside. Okay.
Yeah. Yeah. Absolutely. We could do that. Yeah. That would amount to the same thing as you say. So Right. So what I'll do now in the remaining, I don't know, do I have like, how many minutes do I still have? Okay.
About 15 minutes.
Okay, great.
Wow.
That's great. Yeah, that should be perfectly fine. So you can decipher this definition if you like, and you can write it out explicitly if you choose a basis in your C-star algebra B, and then write out the relations in terms of the basis, and I'll show you some examples. Just to begin with, if you take a classical graph, then remember that gives us a quantum graph by just looking at functions on the vertices and taking the adjacency matrix as our operator. And in this case, the construction on the previous slide gives you this free Cuntz-Krieger algebra. So in a sense, these liberated Cuntz-Krieger algebras are a special case of the construction we're looking at, and they are precisely what you get if you look at classical graphs or just 0-1 matrices. I think I've written out, yeah, so the proof of this is not very hard. In a sense, as I said, you just need to write out the universal properties and then decipher the formulas, and then you'll get that. So let's not worry about this. Let me rather tell you about two examples where something interesting happens. And the first one being the trivial quantum graph on a full matrix algebra. So let me just remind you that this consists of the matrix algebra, its canonical trace, and the identity matrix. So that's perhaps the easiest thing you can look at. But still, the algebra that comes out of this is already somewhat interesting. So if you decipher this complicated definition that I showed you, what really happens is you get the following. The algebra associated to this quantum graph is a universal C-star algebra generated by generators Sij, which you can think of as a matrix of elements. And there are two conditions. The first one is that this matrix is a partial isometry. So in a sense, we have a C-star algebra generated by an n by n matrix partial isometry. And the other condition is that this isometry should be normal. So S star S is equal to SS star. If n is 1, then this is just saying that we're looking at functions on the unit circle. So that would be what you get. But in the case of higher n, being normal doesn't mean that your S is a unitary. So that's perhaps slightly surprising. Let me tell you what we can say about this algebra. So first of all, as I said, I mean, the algebra is, this S is not necessarily a unitary, but you can map it to the universal algebra generated by a matrix unitary, which is also known as Brown's algebra. And since Brown's algebra is well known to be non-nuclear, this in particular means that this quantum Cuntz-Krieger algebra is non-nuclear. You also can check quite easily that the algebra we get is not unital. And in conclusion, this means that this thing is quite far away from being a Cuntz-Krieger algebra, a classical ordinary Cuntz-Krieger algebra. What is it really? Well, what we can say is we can give a relatively convenient description of matrices over this algebra, or rather matrices over the unitization of this algebra. And really what happens is that you get a free product, a unital free product of functions on S1 unitized and n by n matrices. And really, if you like, the copy of functions on S1, that's in a sense the leftover of the ordinary Cuntz-Krieger algebra one would get if one were to look at n equals 1. And in a sense, this new bit which enters the picture comes from taking this free product with matrices. Okay, I won't get into the details of that, but basically what one can check from this is that the algebra is still KK equivalent to functions on the unit circle. So in a sense, we have replaced our vertex by a matrix algebra, but that changes our algebra, but it only does so up to KK equivalence. So we don't get any different K theory in this way. Okay, now that was in a sense the easiest possible example of a quantum graph. And let me show you the next easiest thing, namely looking at the complete quantum graph. So we take the same setting, B, a full matrix block, the standard trace on that, but we take the adjacency matrix, which is given by first taking the trace and then multiplying by n squared. So yeah, don't worry about this multiplicative factor. That's just to make it fit this sure orthogonality, sure idempotent condition.
Do you multiply by the identity or something?
Yes. So this is now multiples of 1 inside. Yes, I guess I should have. Yeah. So viewed as multiples of the identity, this expression. Okay, again, if you write out what this algebra is, you get an explicit description in terms of generators and relations. The first relation is unchanged. It's saying that we're looking at the universal algebra generated by a matrix partial isometry. But the second condition changes. The second condition, the Cuntz-Krieger relation changes because we're looking at a different adjacency matrix. And well, if you stare at this condition for a little bit, you may see, or you may notice that you can map this to another well-known algebra, which is related to this story. And more precisely, you can map this C-star algebra to the Cuntz algebra ON squared. So taking n squared generators and basically even mapping the standard generators to the standard generators, but again, one has to adjust by multiplying with a certain factor, which, yeah, shouldn't worry too much about. And it's easy to check that this satisfies the defining relations. So we have written out the computation here. So this first condition, using the relations in the Cuntz algebra, we see that yeah, the phi s of ij satisfy the matrix partial isometry relations, and also the Cuntz-Krieger relation is satisfied because of the relations in the Cuntz algebra. Okay, and that is what you get by staring at it for a little bit. And when we discovered that, we thought, well, that's probably as much as we can say about this example. And then, in a sense, we well, took a little detour and I used some ideas coming from quantum information and unitary error bases, and played around with these algebras, and tried to gain more information, and then eventually found that that actually this map is an isomorphism, which to me, at least when we started this, seemed totally unlikely. I mean, I didn't expect this at all. So, and it seems very surprising still to me that this is the case. So the key thing is that the way this proof works uses ideas, as I said, from unitary error bases and monoidal equivalences. So some ideas which are not really part of the problem here. And what comes out of this is that we get this isomorphism. So in a sense, this algebra here is a complicated way of writing the Kuntz algebra ON squared. Yeah, what we can do is, in fact, we can prove a slightly stronger statement. So as I told you, one can vary the trace and look at more general delta forms. And as long as this parameter squares to an integer, we still get the Kuntz algebra. But in general, we don't know. At least we don't have a proof. It seems plausible that these algebras are always isomorphic to Kuntz algebras, but in order to prove that, it seems one would have to find a different proof, a different approach to proving this, which I would find very interesting. So if someone has any ideas how, well, maybe see more directly why this is the Kuntz algebra, please let me know. And I think that's all what I wanted to say. So thanks very much.
Thank you very much, Christian. Are there any questions or comments? Let's see, Elizabeth wants to ask a question. Please go ahead.
Hi, Christian. This is really interesting. Thank you. I was wondering about how important your unital assumption is throughout, because of course you can have non-unital Cuntz-Krieger algebras.
Yeah. So actually, yeah, that's a very good point. So when we started out, we thought, okay, so Cuntz-Krieger algebras associated to finite matrices are unital. So maybe we should also have a unit condition in our setting. And in a sense, we couldn't quite make sense of that. And then this example of the trivial quantum graph that I showed you kind of suggests that one probably shouldn't put such a condition. So yeah, it seems that the unit is something which just happens in classical Cuntz-Krieger, but which doesn't happen very often in this setting, if that makes sense.
Maybe can I rephrase then that you don't, if you started by trying to find a quantum model for a non-unital Cuntz-Krieger algebra, would you make any changes?
Good question. So you mean a classical non-unital Cuntz-Krieger algebra? So I don't know. I mean, in a sense, yeah, going here to infinite matrices is tricky. and we haven't really thought about that. So I'm not sure.
So for example, a graph in question would be A infinity, which gives compact operators. So what Elizabeth is asking is for a non-commutative analog of the compact operators.
I don't know. The trouble is, so there is, I showed you these two pictures of quantum graphs, one being this quantum adjacency matrix, and the other one, Weaver's picture, where you take subspaces in some phenomenon algebra. Weaver's picture makes perfect sense for infinite dimensional graphs, or you can phrase infinite dimensional quantum graphs in that picture. But it seems less clear how to translate back to get a matrix from that, and then to cook up a definition. So that's something that, yeah, I just don't know. But it would be interesting to see if one can do something.
Thanks.
So are there other questions? I have one. In the previous example, not the one that gives a when, but the previous one, it reminded me of in this thing that so say you want so how does one say to show, so you take the functor that associates to an algebra the set of homomorphisms from the algebra to Mn, the n by n matrices over the complex numbers, right? And then you want an algebra, you want to say that this functor is representable, so that it is represented by, so you can write that as home of some algebra into C. And that algebra is so you write for each A, you should have a matrix Xij of A, which satisfies, I mean, the relations that say that the mapping A to the matrix of the Xij is a homomorphism, right? And so in general, this can be generalized to, I mean, instead of maps from A to MNC to other subalgebras of, of MNC, or some direct sums, finite direct sums of such things. And this kind of algebra is what you representative of a functor is to matrices is what you find when you write your conditions to be in that certain matrix with coefficients in the algebra you are defining satisfy a certain relation. So I thought, I mean, how far this analogy could be carried outside of that particular example.
So we certainly haven't thought about it that way. Yeah. So I guess answer right now is I don't know, but yeah, something to think about. So yeah, in a sense, it would be nice to understand more or better the structure that we produce in this way. So of course you can always generalize things. There is plenty of structure results for Cuntz-Krieger algebras, and you can ask analogous questions here whether one can classify or at least describe the structure. It seems, at first, it seems unlikely that you can do that in general, but at least the two examples that we have looked at in some detail, one can say something, at least a little bit. And yeah, it would be, so I'm not sure. It could be that still in general you get just too much and it's hard to get anything, but well, I don't know.
But so, for example, you've shown an example of a non-nuclear, non-simple, etc., non-separable sister algebra.
It's separable. It's separable.
Separable, yeah, okay. And then another which is a Kirchberg algebra, or when.
Yeah.
So it's what would be interesting is a condition to put so that when the algebras you produce are necessarily Kirchberg or the opposite, I don't know.
Yeah, so and this is probably related to the fact that you have these kind of free products floating around, or you can at least get some sort of free product structure, which of course immediately destroys nuclearity and all sorts of nice properties. And then you have these Kirchberg type behavior. And it's, yeah, it would be interesting to understand. Like,
but KK wise, if you do Kirchberg, if you do coproducts, is, I mean, not very different from tensors, right?
Yeah.
From direct
exactly.
sums, I mean, from direct sums.
Exactly. So on the level of KK, one should not see the difference too much. But remember, I've only looked at the two simplest examples of quantum graphs, and there is a lot of flexibility, and there's a continuous parameter in a sense in which you can change your quantum graphs. So it's not so clear what happens in general. So that's
do we have any questions from our quantum list, the quantum audience?
No, I'm sorry. I'm trying to understand the general picture. I know.
Hi, Gaston. Good to see you.
Hi. How are you?
Yeah,
Good to see you too.
not too bad. Thanks.
No, I'm too algebraic for that. I'm trying to get the main ideas. And I'm trying to understand if I can use this kind of constructions for algebraic quantum groups. I mean, the algebraic groups, quantum groups coming from coordinate algebra of algebraic groups, but I don't see it clearly. I think it's very interesting, but I don't get it. I think so.
So this relation to quantums, I mean, I didn't say anything about it, but so I guess the most obvious connection is to quantum permutation groups, and that Banica and Bichon studied. So quantum automorphism groups of graphs, where you take one's quantum permutation group, and then you look at quantum subgroups of that, in a sense, encoded by graphs, and it turns out these are interesting, fascinating Hopf algebras, and there's tons of questions that one would like to understand better about these Hopf algebras. For instance, finding an example where this Hopf algebra is non-trivial, but has no, the abelianization is trivial. So that's not known, and there is a lot of apparently easy to formulate questions, and you have, I mean, generators and relations and a pretty explicit description, and still it seems very hard to answer these questions.
The presentations are very explicit and seems to be easy, but it's not really the case.
Yeah,
that's true.
It's an interesting story.
When you take the matrices, and the examples where with the entries 0s and 1s. So on the other matrices, you take integral values. What happens if you take the very well-known Cartan matrices? Does the examples produce something like a leaf, flavor, or coordinate algebras or something like that, or you don't know?
I don't think so. So if you were to allow entries different from 0 and 1, that would in graph language, I mean, just say that you allow multiple edges.
Yes.
And classically, of course, you can do that, but in the quantum setting, it's not so clear how to phrase that condition algebraically. So in a sense, I don't think this is known. So one would first have to find out how to write that. And as I told you at the start, a lot of questions.
Yeah, very nice. This is nice to have a lot of questions.
One question that I had, in the classical setting, you can define your Cuntz-Krieger algebra by matrices of zeros and ones, but also by a matrix with other integer, non-negative integer values. Is there, so that, I mean, it has an associated graph where, say, I like to think of ON as associated to the 1 by 1 matrices, matrix which has an n. You can also think of it as the matrix associated to the full all ones. Is there such a translation from one thing to the other in the non-commutative setting?
I think, yeah, exactly. I should have mentioned that. So of course, these Cuntz-Krieger algebras are graph algebras, so you can view them as associative graphs. And in the ON case, the picture, the standard picture would be to have just one vertex and n loops. And the relation between these graphs and the graphs that we are looking at here is passing from any graph like this n loop graph to its line graph. So where you replace the vertices of the line graph are the edges of the original graph, and the adjacency relation is determined by how these edges connect or do not connect. So yes, you can pass from these graphs in graph algebras to these simple graphs here, and that's by passing to line graphs. And then you always get, by the way, you get these simple graphs, so at most one edge. So
yeah, but I mean, what I mean is, well, you cannot handle. You say you cannot handle matrices with entries other than zeros and ones, but you can, in fact, if you can associate to one such to a matrix with not zero, which doesn't have zeros and ones, one that does. Perhaps that makes sense in more generality.
In that way, yes, but if the matrix that we're putting in here, one could also ask, okay, one can look at more general entries and how could that generalize?
Yeah, so the question is this surely important condition, because I mean, so if you have a graph with a source and range and whatever, there are two matrices, so there is an associated map. So how is this? So you can associate to a map between finite sets, a map between the free abelian groups they generate. So say the map is F lower star that goes in the same direction and F upper star that goes in the opposite. And if there are, so you have your graph with R and S, the range and the source function. And if you do, I don't recall exactly, R upper star, S lower star, or if you do S upper star, R lower star, then one way you get one of the matrices, the one with the zeros and ones, and the other way you get the other one. And perhaps, I mean, I don't know. There is this indicates that there is some equivalence between which matrices come from or can be linearized and which might translate in your setting into another way of phrasing the this Schroeder impotent condition. I don't know.
But a question, you can construct such as algebras for any graph, is that right? Or you need the graph should be simply connected, or I don't know, with simple lazy.
Well, I mean, yeah, just simple in the sense that they should have just at most one edge between.
Okay, simple laced, we say that in Lie theory. So you can associate an algebra to any simple laced graph of a Coxeter group, say.
Yeah, but I think the Dinkin diagram picture is probably misleading. So I would imagine you get something not very interesting if you look at. Yeah.
So the ON with the orthogonal, I associate the ON with the orthogonal group, but it doesn't appear. It's not the ON appearing here. It's not.
No. The O is for the Kuntz.
Yeah.
No, I don't think there is a deviation there.
Okay.
It's just a coincidence.
It's always in Kuntz.
Yeah. A very nice talk.
Okay, so are there any more questions? So if not, I will stop the recording.